In this video, we're going to see an example of how I can use the method of Laplace transform to solve a particular differential equation. This equation is that the fourth derivative of y minus y is equal to 0. And then I have four different initial conditions: y of 0 is 0, y prime of 0 is 1, y double prime of 0 is 0, and y triple prime of 0 is 0. So how can we use Laplace transforms to solve this? The first thing I'm going to do is I'm going to define that the Laplace transform of just this function y of t, I will give that the name capital Y of s. The way this method is going to work is I'm going to apply the Laplace transform, which is going to convert this differential equation into an algebraic one. I'm going to solve that algebraic equation, and I'm going to try to use the method of inverting my Laplace transform to get back to a solution to this initial value problem. All right, so let's apply the Laplace transform to our equation. The first thing I'm going to have to do is recall what the Laplace transform of a derivative does, and it works as follows. If I have four derivatives, I get an s to the fourth out the front, and then it just becomes y of s. Then I have a cubic term in s, I subtract off s cubed, and then it's y of 0. I subtract off an s squared, I get a quadratic term in s, which is times y prime of 0. I subtract off an s times y of 0. I subtract off an s times y double prime of 0. And then finally, I subtract off y triple prime of 0. So all of that is what the Laplace transform of the fourth derivative is. Then I have to subtract off y, and the Laplace transform of y is the Laplace transform of y, and so I just subtract off y of s. And on the right-hand side, the Laplace transform of 0 is just 0 once again. Now, thankfully, my initial conditions are relatively nice, and I think the only one that's a prize is y prime. So this one's going to go to 0, that one's going to go to 0, and that one is going to go to 0. And as a result, what I will do if I clean this up a little bit is I get s to the fourth, y of s, minus s squared times 1, y prime of 0 happened to be 1, that was the only one that was non-zero. And then subtract off a y of s, and this is equal to 0. Now I have an equation that is an algebraic one, and I want to solve for y as a function of s. This is relatively straightforward. The only thing that doesn't have a y in it is this s squared, so if I leave y of s on the left-hand side, on the right-hand side I'll move that minus s squared to become a positive s squared. And then the coefficients of the y of s are going to be an s to the fourth, and so I'll put that there, and then I also have a minus 1 for the other term. So this is what I have. Now, even though I've solved my algebraic equation, I don't actually yet know how to find the inverse Laplace transform of this. So the first thing I want to do is a little bit of algebra to hopefully manipulate this answer into a format where I can take the inverse Laplace transform. The first thing I'm going to do is look in the denominator, and I actually note that I am able to factor that. In the denominator, so copied and placed the numerators, I'm not going to make any changes there, is nothing but s squared minus 1 multiplied by s squared plus 1. It's a difference of squares, the s squared and the 1. Giving myself a little bit more space to work with here, I'm then going to factor even further by noting that the s squared minus 1 can be written as s minus 1 times s plus 1. And then for the s squared plus 1 term, there actually isn't anything that I can do further. This term over here is irreducible. What that means is that if you tried to factor it as the product of two linear terms, you could not do it where those constants in the linear terms were real numbers. Now, this is all lovely, but I still don't know how to do the inverse Laplace transform of this. So what I'm going to do is apply the method of partial fractions, and I'm going to convert this expression into a new format, which hopefully I will be able to compute the inverse Laplace transform of it. So what my standard guess is going to be is that I'm going to write it as an a over s minus 1, the first linear term, as a b divided by s plus 1, the second linear term, and then as a cs plus d as in a generic linear term divided out by that irreducible quadratic divided out by s squared plus 1. Now, I know you love solving linear systems, so if you wish, you can pause the video and go off and do that. However, I've just done it for you quickly here. Basically, we had taken this long expression and we plugged in a bunch of different special values to solve for the a, the b, the c, and the d, and I invite you to pause and review that work. Now, for the purposes of finding the inverse Laplace transform, what are we supposed to do? I've computed that the a, the b, the c, and the d are these four values, And so what I am thus trying to compute is going to be equal to a, which is 1/4 divided by s minus 1 plus b, which is a negative 1/4 divided by s plus 1, a 0 times c, and then plus a d of 1/2 divided by s squared plus 1. So what my actual goal in this video is to do is to compute the inverse Laplace transform of that. Now I've finally written it in a reasonable way. What I mean by that is I have written this thing I want to compute the inverse Laplace transform of as a linear combination of things that I know the answer to. 1/4 over s minus 1, well, the 1/4 comes out the front, and the inverse Laplace transform of 1 over s minus a is just e to the value of a, so in this case, e to the t. Then I have a minus 1/4 term, and now it is in, if I want to have it as 1 over s minus a, the a now is minus 1, so it's an e to the minus t term. And then 1/2 over s squared plus 1, that just looks like a sine term. There's a 1/2 out the front, so I'll bring it up there. But then this is just a sine of kt with k equal to 1, and thus a sine t. And so what I have computed here is the y of s, and this is just going to be this following expression. So zooming out here, I see that I have actually 4 stages. The first stage is where I took a differential equation and converted it by the application of the Laplace transform to an algebraic equation. And then I took that algebraic equation in the second phase and solved for y as a function of s. I solved the algebraic equation. The next portion was a long portion where I did a bunch of algebraic manipulations. In this specific case, it was partial fractions. And the goal of that algebraic manipulation was to take the solution to the algebraic equation and write it in a format that was compatible with me taking the inverse Laplace transform easily. And then after it was written in this nice manner, I went and computed the inverse Laplace transform. So the broad idea here is that there's always this differential equation world and there's this algebraic equation world. The Laplace transform and the inverse Laplace transform convert between these. So you start with the differential equation, you convert it to an algebraic one with the Laplace transform. You solve that algebraic equation and perhaps do some algebraic manipulations to clean it up. And then you convert back to a differential equation and now you have your solution to your initial value problem.